So we're going to look at doing our radius of convergence and interval of convergence tests, but we're going to do this in the context of our Taylor series. So we're going to first of all generate our Taylor series, and then we're going to come up with our general formula for our series expression, our sigma notation, and then we're going to do our ratio tests for radius and then test the endpoints for our interval of convergence. So the first thing we need to do is generate our Taylor series. So I'm going to generate my p of x function. Okay, so p of x is equal to, so a1 is going to be the log c. Okay, and log c is 1, so we get log 1, which is 0. So that will be our first term of that expansion. Our a2 expansion is going to be 1 over c. That's going to be our coefficient. And maybe I should put here, maybe I'm going to do a0. Let's change that to a. We're going to start from 0. a1. So this is going to be 1 factorial. And then it's going to be x to the power 1. Okay, so when we plug in c equals 1, we still get 1. So we end up with 1x. Okay, so then we move on to the next term. So a2 is going to be negative 1 over c squared. And then it's going to be x squared. I need my 2 factorial divided by 2 factorial, and then it's going to be x squared is my power series part. So when I plug this in, I'm going to get negative 1/2 x squared. Okay. Moving on to the third term, okay, using my Taylor theorem 1, I'm going to again generate my a3 coefficient by taking the third derivative. So it's going to be positive 2 over c cubed. Okay, I'm just going to zoom in here. That's c cubed over 3 factorial. Okay, so there's my coefficient. And then the power series part's going to be x cubed plus dot, 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 dot. Okay, so at this point, well, I kind of know the answer to this, but I think you guys can kind of see, based on the first 3 terms anyways, this is really just an alternating series for the an term. Okay, and then the power series is just going to go up by n. Okay, so there's my coefficients. I'm going to generalize the formula then. So I know that my f of x is going to equal the infinite series from n equals 0 to infinity. And this is going to be 1 over n. So that's going to be my coefficient part. So I'm just going to maybe highlight that. Okay, my coefficient's 1, 2, 3 like that. It's going to be 1 over n. Okay, and it's alternating. So in the numerator, I'm going to have negative 1 to the, so start with positive. So I'm just going to leave that as n, 1 over n. Okay, so that's now alternating. Okay, and those are my coefficients here. And maybe I should include that negative there. N equals 1. No, sorry, I need to do n minus 1 or let's do n plus 1 since we don't want to go 2. Okay, so n plus 1. Okay, so that's going to give us alternating terms with the right positives and negatives. And then it's going to be x to the power n is a power series part of that. Okay, just double checking when n is 1. Okay, well, I suppose I could have started at 0. Let's actually start this at, let's start it at 0, and then we can just use it n plus 1 like this. Okay, n plus 1. Okay, just double checking that all our things match. We could have started this at 1 and made that just n as well. So there's my general formula for my series n. And then now I can apply my ratio test to test the interval of convergence. Okay, so I'm going to apply my ratio test. So this is now the limit as n approaches infinity. The ratio test is going to be negative 1 to the power n plus 2, x to the power n plus 2 over n plus 1. Okay, actually this is going to be n plus 1 as well because we can't have divide by 0. So we're going to make that n plus 2. Okay, and then we're going to then divide all that by negative 1 to the n plus 1, x to the n plus 1, all over n plus 1. And we're going to let n go to infinity, and we need to know when those values are going to be less than 1. Okay, so then I'm going to simplify this. So simplifying this expression, I'm going to end up with limit as n goes to infinity, and I'm going to group my terms. So I'm going to have negative 1 to the power n plus 2 over n plus 1. So I'm just going to end up with 1, negative 1 there. N plus 2 divided by n plus 1 for x's, just going to leave me with x to the power 1. And then I'm going to group the n terms. So I'm going to end up with divide for n plus 1. N plus 2 is divide, so that ends up in the denominator. And I'm going to let the limit of that go to infinity. So at this point, I know that's going to go to 1. So I'm going to end up with negative x, absolute value, is less than 1. Okay, so my radius of convergence is 1, and I know the center of my convergence is 0, so then I know my interval so far is going to be negative 1 to positive 1. Okay, now these need to be tested. We need to test both endpoints. Okay, so then that's our next step then. We're going to test the endpoints for the radius to determine if they're included in the interval of convergence. So to do this, we're just going to substitute this into our original series. So we're going to let x equal, to start with, negative 1. So we're going to test x equals negative 1. And what does that look like when I plug it in? So I'm going to end up with my series, infinite series, and equals, what did we start at, 0 or 1? I forget, 0. 0 to infinity. And it's going to be negative 1 to the n plus 1. It's going to be x, or negative 1, for x to the n plus 1. And that's all divided by n plus 1. Just double check that. Yeah, that looks pretty good. So this is going to end up being 2n plus 2. So we're going to end up with our negative 1 to the 2n plus 2, which is always positive. So this looks like this. N equals 0 to infinity, negative 1 to the 2n plus 2, all over n plus 1. Well, that's going to be always even, so it's going to be positive. So we know that this is a harmonic series that doesn't alternate, so it is divergent. Okay, so we know that for the left-hand endpoint, okay, so for x equals negative 1, we're going to say that, yeah, it's divergent, so we're going to keep that like that. So then we go ahead and test the other endpoints. So we're going to test x equals 1. Okay, so I'm going to plug that into my series formula, n equals 0 to infinity, negative 1 to the n plus 1, 1 to the n plus 1, over n plus 1. Okay, so now in this case, that's just going to be 1. Okay, so we're going to end up with the negative 1 is going to allow us to alternate. So now we have an alternating harmonic series. We know this converges. Okay, so if this converges, then we know that this endpoint here must be equal to, we can include that endpoint, so we now have a closed interval on the right hand side there. So my interval of convergence then is, when I do this all out, so the interval of convergence works out to be from negative 1 to positive 1, including positive 1.